In previous sections, we discussed closed interval method to find maximum or minimum of a function defined on closed interval. So this method has some application in many areas. So we will follow those steps. So all the problems in this section are word problems, some long sentences. So you read the problems very carefully to figure out what's the situation, what you are looking for, what's given, and so on. And sometimes a diagram is useful. So reading the problem, you want to use your letters or variables to indicate quantities that are given in the problem. And you establish equation between those quantities. And then in the next step, you solve the equation or use the equation to express the main function that you are after in one variable. And then now that you have function, you apply the closed interval method to find absolute maximum or minimum. Probably you need to be creative to equate your quantities or solve the equation for the main function. So in step 2 and 3, you need to be creative. All right, this problem is about rectangular field. So we have some field with area 6 million square feet. So here capital M is just a million. And for this rectangular field, we want to divide it in half by putting extra fence, which is parallel to one of size. And then you want to minimize the fence amount to minimize the cost. So in the first step, we have read the problem carefully and then drew a diagram like this. In the second step, you use your letters to indicate quantities. Well, in this rectangular field, we need length and width. You can choose your own letters, of course. And the condition says the entire area must be 6 million. So area is going to be L times W, which is 6 million. Good. And we are also interested in the amount of fence or length of fence. Now that this is parallel to this width, this length is again width. And then length of fence. So we are interested in this. Of course, we need 1, 2, 3 copies of W and then 2 copies of L. So we are interested in minimum of this function. Now that we have 2 variables, you want to eliminate one variable using this identity. Then eventually we'll have function in one variable, then we'll be ready to take the derivative and find the minimum. So let's say this is a function f. So then f becomes 3. So then f becomes 3w plus 12, but you want to determine which variable you want to eliminate. Well, if you want to eliminate w, you solve this for w, which is 6 million over L. So you replace w by this guy. So 6 million over L plus 2L. So now this is a function in L. So f of L. Good. Again, here m is just constant, 6 million over L plus 2L. Okay. So we are done with the second step, and third step is to take derivative. So you take derivative with respect to L. Again, this M is just constant, so 3 times 6 million, and we have L to the negative 1. So derivative is negative 1, L to the negative 2 plus 2. So we have derivative like that. And then we are interested in the minimum of f. So we want to find where. So we want to find where this f prime becomes 0. So we solve the equation. So we have 6 million over L squared plus 2 equals 0. After reducing, we have 9 million over L squared equals 1, or L squared is 9 million. And 9 million happens to be square of 3,000. So that says L is 3,000. So far, what we have found out is that this function has 0 derivative when L becomes 3,000. But there are 2 cases. One is maximum, one is minimum. So our candidate, L equals 3,000, can give us either maximum or minimum. So we want to make sure that this is indeed the minimum. So we can use first derivative test or second derivative test. Remember, we studied 2 types of method to make sure this gives us maximum or minimum. So let us use second derivative test. Second derivative of f is derivative of this, which is 6 million and 2 L to the negative 3. So this is second derivative, and we want to make sure this is the case. And we want f double prime is positive, right? F double prime positive will have concave upward. F double prime negative will give you concave downward. And actually, f double prime at 3,000 is, well, no matter what it is, everything is positive, is definitely positive. So second derivative test says that we have this case because f double prime is positive. As we expected, L equals 3,000 gives us the minimum. So the length of the side is 3,000. That will give us the minimum cost. So L is 3,000.